This video, we're going to prove the following fact. If H is a subgroup of G, and A is an arbitrary element in G, and we let the said aHa inverse be the set of all elements where H is in H, such that aHa inverse is in this set, then that set is a subgroup of G. If you like watching mathematical proofs of facts like the one in front of you, please subscribe to my channel. Okay, so to show that this set is a subgroup of G, well, first of all, it is a subset of G because A is in G, H is a subgroup of G, so little h is in G because little h is in big H, and A inverse is in G. So this whole set is in G regardless of which H you pick. Because basically this H is in G. It's a special portion of G, but it's in G. Okay, so we want to show that this subset of G is in fact a subgroup. So we need to show that things are closed and that each element has an inverse. Okay, so how about we let X and Y be in aHa inverse? That implies there exists H1 and H2 such that X is aH1 inverse and that Y is aH sub 2 A inverse. Now we need to show that X times Y is also in there. Well, this is X, another way of writing X, and this is another way of writing Y. I can bracket it that way, so I get aH1 times E times H2A inverse. Can bracket it that way, and that's just A1H1 because this times E is just this times that. H2A inverse. Well, this is A times H1 H2 A inverse, but H is given to be a subgroup. So if H1 is in H and H2 is in H, since H is closed, H1 times A2 is in H. So this certainly is in aHa inverse. So we have closure. Now, we need to show inverses. Now, for example, if you take X and Y and you claim Y is X inverse, well, to show that, you need to get the ID element. If X times this is the ID element, then that implies that Y is X inverse. But you need to know the ID element first. So although we don't have to prove that there's an ID element, we have to know what it is. And I claim that aE A inverse, remember H is a subgroup, so E is in H, is the ID element. Well, let's see. I'll take aHa inverse, where H is in H, and I'll multiply it by what I'm claiming is the ID element. In reality, that's just E. So you have aHa inverse composed with E. That's just aHa inverse. That is, we got back what we started with. If you want to do it the other way, it's not going to matter because that's just E. aHa inverse, you don't need to say the E, and A times A inverse is E. So this whole mess on the left is E. So it's E times aHa inverse, which is aHa inverse. So we do know what the identity element is. It's aEA inverse. You really can say E is the identity element here, because it's not in the right form. It's not in the right form. Okay, so now that we know this, we have to show inverses. Let H be in H, which implies H inverse is in H. Now, consider the following. aHa inverse times aH inverse A inverse. I claim that this here is the inverse of that. So we get aHa inverse times aH inverse A inverse. That cancels out the E, so we have aH H inverse A inverse. This cancels out to E, so we get aEA inverse, and that is the identity element in a capital H A inverse. So yeah, we do have inverses. So inverses exist in aHa inverse. Okay, therefore, because we have inverses and closure, therefore aHa inverse is a subgroup of G. And that completes the proof. Just a matter of checking closure and inverses. But again, you have to know what the identity element looks like before you can talk about inverses. See you guys in the next video. Please subscribe to my channel, click the like button, leave a comment, tell your friends, family, and enemies about my channel. Watch and learn.